Alright, let's start lecture. We'll finish one little bit in terms of interference, and then we'll move on to another concept related to the gear, okay, gear train and gear forces. Alright, so in previous lecture, we talked about the phenomena of the interference. In short, basically interference happens when the contact length, which is the length AB, okay, is outside the CD, which are the tangential points of the base circle and the pressure line. Okay, so if your contact points outside the CD, then you will have interference. And the idea is always to avoid interference. So how to avoid interference then? To avoid interference, one way is to have this so-called undercut. So if you have this undercut here, then you will remove the possibility of this interference. And that generally naturally happens when you are using the hobbing process, using a cutting tool. That'll basically remove the material if there is interference. Now, however, there are some other hard requirements that you can do to avoid interference. So those are a bunch of the formulas you can make use of, okay, in terms of trying to avoid the interference. So, for example, if gear ratio is 1 to 1, okay, then the smallest number of teeth to avoid interference is this. Smallest number of teeth on the pinion . To avoid interference, let's say we call NP, and the formula is this. So 2K over 3 sine square phi 1 plus root 1 plus 3 sine phi square. Okay, so that's the smallest number of pinion teeth on the pinion that you can have in order to avoid interference. The phi here is the pressure angle, okay, and the K here is a value corresponding to the type of teeth. You know, whether you have full teeth, full tooth, or stub tooth. Okay, and for full tooth, which we generally use in our case here, the K is just equal to 1. All right, yeah. So you plug in this phi, you plug the K, you'll get the NP is 13. Okay, so the smallest number that you can avoid interference, physically no interference at all, is 13 when pressure angle is 20 degree. Okay, yeah, and also for gear ratio 1 to 1. Okay, yeah. So that's the first one here. Now, if the gear ratio is not 1, okay, let's say if the gear ratio, let's say we call that M as NG over NP. Okay. If it is greater than 1, okay, now your smallest number and the pinion to avoid interference is a slightly different formula now. Okay. Is this. So NP equal to 2K over 1 plus 2m sine square phi, and then m plus root m square, a bunch of things m here, 1 plus 2m sine square phi. Okay, yeah. So that's your NP. Okay, yeah. Now, when gear ratio is not 1, okay, you also have, not just for the smallest number of teeth for the pinion, you also have a constraint which is the largest number of teeth for the gear. Okay, so for this case here, you also have another condition. Okay, there's the largest number of teeth, okay, for gear. Okay, for the gear. Which one did you Is that okay? Yeah, okay. And that number is NG. Sorry, NG, yeah. So it's NP square sine square phi minus 4k square over 4k minus 2np sine square phi. Okay? Yeah, so that's the two conditions. Basically, you use them together when the gear ratio is not 1. Okay? Yeah. So let's say, for example, right, if phi equal to 20 degree, okay, then if I plug it, if phi equal to 20 degree, let's say if I set NP equal to 13, okay, 13 teeth. Okay, if NP is 13 teeth, then the NG can be calculated using this formula, right? If the pinion is 13, the NG is calculated actually 16. Okay, so which means what? Which means when you have a 13 teeth pinion, then the maximum number of teeth for the gear to mate it is 16. Or in other words, the maximum gear ratio that you can achieve without for the node interference case is 16 over 13. So it's less than 2, right? Yeah. So that's the idea here. Okay. And you can keep punching the numbers there. And actually, when it reach 18, you will see that the NG just becomes infinite. Okay, yeah. So what does that mean? That means when the number of teeth on the pinion is 18, you can use a gear with an arbitrary number of teeth, okay, to mate it. So the gear ratio is keeping any. Okay, yeah. So in the lecture notes, there's a table. You can basically it's a listing of conditions based on the formulas that we just calculated over here. Okay, yeah. The other thing is, I don't have the picture here. The other thing is that when you have a different pressure angle, okay, when you have a different pressure angle, let's say when you have a phi equal to 14.5 and phi equal to 20 degree and phi equal to, let's say, 25 degree, what's the effect of this pressure angle on the gear tooth? Okay, so let's I will just roughly draw the gear tooth at here. Okay, so the effect is, if you remember, the base circle radius. The base circle radius is equal to what? The pitch circle radius times cosine phi, right? Times cosine phi. So when phi angle is increasing, what do you think of the base circle radius? Would that be decreasing or would that be increasing? When phi is increasing. When phi is increasing, the cosine phi, what's cosine phi? This is between 0 and 90 degree, right? So cosine is decreasing. So in other words, the base circle radius is decreasing. So if the base circle is decreasing, so if for this case here, the base circle is probably here. For this case here, the base circle is probably here. And then for this case here, the base circle is probably here, right? Yeah. So the fact that, remember, where does the involute profile generate? It's generated based on the base circle, right? So when the pressure angle is bigger, you have more involute profile, basically. Okay? Yeah. So you can imagine that if I talking about the smallest number for the pinion to avoid interference, okay? When phi is 20 degree, the smallest number to avoid interference, the NP is 13, right? It's 13. Okay, yeah. So for this one here, the smallest number to avoid interference, what would you expect? Should I be bigger than 13 or smaller than 13 now? Because the possibility of getting interference is actually chances smaller. Because why? Because you have a more envelope profile than this one here, right? Yeah. So this is actually going to be a smaller number. Okay, it's roughly a 9, okay, or 10. Okay, yeah. So that's the idea of the pressure angle. Okay, the effect. Okay, so that's basically wrap up with most of the terminologies and some things regarding the gear. There are a lot of mathematics actually going on behind these things here. So we can't get into all the details, right? But if you're interested, okay, actually, for people who in the gear design business, right, you will definitely require to go into that much of details. Okay. So let's talk about now gear train and the gear forces. And then this first concept is gear ratio, which we actually already talked about already. Okay, so let's say you have a pinion, okay, and two gears, okay, driving each other. Okay, so this first one, let's say this is a pinion, okay, and oops, the bottom here is the gear, okay, and you have the n number of teeth at here, and then you have an n g number of teeth over here. Okay, yeah. So let's say this is rotating at n1 and n2. Okay, n1 and n2. Or you can also say this is omega 2. This is omega 1. Okay, angular velocity. Okay. So in literature, generally you have actually two different kind of a way of defining gear ratio. One way, a lot of time people defining the gear ratio is they say call it R here. Gear ratio equal to the output angular velocity over the input angular velocity. Okay, that's one way of saying it. Okay, yeah. In this particular case, your angular velocity, okay, is always inverse proportional, to the number of t's there. So np over ng. Okay, np over ng. That's one way of saying it. Okay. In other cases, or in our class, I think most of the time what we do is we say the gear ratio we'll just simply use this. Okay, so np over ng. Okay, so it's actually the two they're just inverse of each other, right? Yeah. All right. Yeah. The first one is just the inverse. The first one is to use the output velocity, angular velocity, over the input angular velocity.
But we're going to use the bottom one?
Yeah, we're going to use the bottom one, generally. Yeah. Okay. Okay, so gear train. Gear train is particularly in kinematics. It's an easy way to, and then also it's useful when you do some mechanical system modeling. Okay. So gear train. Let's say I'll draw a gear train at here. Okay. There's one gear here. Let's see, another gear. Okay. And then you have a small gear here. Then you have a bigger gear here. So in the end, you have one more gear at here. Okay. So let's say this is a gear train. Okay, there's a gear train here. So what does that do here is, let's say label some of these numbers here. So let's say this is called N2, This is N3, number of T's. Okay, N4. Sorry, this is N5, and this is N4, N6. Okay. So number of T's for each one of the gear. In the center here, there's always a shaft, right? There's always a shaft here. So the initial rotation for this one here is rotating to this way. Okay. So you can draw the rotations for each one, right? Like that. Okay, so then for this kind of a gear train, we need a value basically, which is what we call the train value. Okay, or the gear train value. So we use a E represent this value here, and the E is defined as positive and negative. Okay, numerator's product of a driving tooth number over the product of driven tooth number. Okay, driven tooth number. Okay. So what does that mean is, right, let's take a look at this particular example right here. So what is the product of a driving tooth number in this case? Which one is the driving gear? This is driving, right? And what else is driving? This one here, was that a driving? That's the driving one, because this is driving this guy here, right? And N4, that's not a driving one, right? Because this N4 here is what we call no, this is not a driving one. N3 is here is what we call is idler basically. Okay, so N4 is connected to N5, this fourth gear and the fifth gear to connect using the shaft, basically maybe on a different location of the shaft, right? Yeah. But N5 is a driving one, right? So N5 is driving N6. Okay. So then your numerator would be N2 times N3, then time what? N5, right? Time N5. That make sense? Yeah, that's the number of T's that belong to the driving gear. Okay. Bottom, driven one. Which one is driven? This is driven, right? This N3. That's why I call it idler, because it's both a driving and it's both a driven. Okay, so N3 is a driven, N4 is a driven, and what else? N6 is a driven one. Okay, yeah. So altogether you have this numerator and denominator. Yeah. What about the positive and negative? That is determined by the direction of a change of rotation in terms of input and output. So in this case, input this direction, output this direction, so we'll put a negative here. Okay? Yeah. So actually you can cancel these two out, right? Yeah. That'll basically is going to be your train value. So what does the train value do then? Your output, let's say your output omega 6 is actually just simply equal to the train value times the input omega. Okay, I guess I call it omega 2 here, right? Yeah. Okay, that's how you do with the train value. So as you can see, actually the train value, which format of the gear ratio is it towards to? Is actually this one here, right? Okay, the train value is this this idea here. Okay, is that good? Yeah. Okay, so we don't really need to go into too much about the kinematics of a gear, but I think as long as you know this simple ideas, of the trim values and gear ratios, that's fine. Okay, yeah. All right. So the next topic is this. I think the other good application of this trim value is, your learning control system. Often one first step is you do a modeling of the system, right? There might be a certain kind of gear trains exist, with the electromechanical system. So when you're deriving an equation of motion in terms of one size, so you have to map the moment inertia, the damping things into one side, right? So how do you map that? You need this trim value. So the e to the power square then times that the thing, will do the mapping. Okay, so next topic, gear forces. So this portion is very important because we really need that in terms of our design, right? Yeah. Let's talk about spur gear. Okay, so in particularly, we'll talk about spur gear first. Okay. So I'll draw a diagram in here. So same thing. Let's see. Okay, we have pinion drives the gear at here. Okay, let's say this is pinion, and this is the gear. Okay, and it does have a pressure angle. Okay, it has a pressure angle at here, maybe 20 degree or maybe 25. Okay, so there's a shaft. Okay, carries these two gears, right? Carries these two gears, and we need to figure out certain free body diagrams. Okay, both for the shaft and for the gear. So first of all, let's look at the free body diagram for the pinion. Okay, if this is the pinion circle here, okay, and what is a force felt by the pinion? So this is the pressure angle, right? This pressure angle. So when the pinion drives the gear, there's action-reaction force. The action-reaction line of action is always along this line here, right? Along this line. So the reaction force, when the pinion pushes the gear pushes it back. So the reaction force from the gear is supposed to be right at this pitch point, and you have a force pushing back at that location, right? With a certain angle, which is the pressure angle here. Okay. So we call this, let's call this W at here, okay? The notation. Okay. So apparently, the W can be decomposed into two vectors. Okay, one is the horizontal, the other is the vertical, radial. So we call this horizontal one WT, and we call this radial one WR. Okay, yeah. So that's what the pinion feel at that location. Free body diagram. Then guess what? Then it has to be balanced, right? The gear basically is carried by the shaft. So the shaft is where the gear is fixed on, the pinion is fixed on. So in order to balance this, then from the shaft, right, you need to have, basically you need to have a force, right, to balance that the W. Okay, the W. Now you just not only need a force to balance the W here, because the particular location that the action of at here, guess what does the WT generate with respect to the center? Moment, right? Actually here we would call it torque, right, because you're trying to rotate it. Yeah. So in order to balance that one, at the location here you need another torque to balance it, which should be the opposite direction. In this case here, it's this direction, TA. Okay. So that's the free body diagram for the pinion. Okay. So there are two folds, as you're going to see later. Okay. One fold is you will focus on this WTWR in terms of gear design. okay, or WWT. Okay, so for the gear design, okay, we're gonna look at this W and WT. Okay, this is basically what matters for the gear design. Okay, but we also have another fold. Another fold here is for the shaft design. See, because the loading condition here, imagine there's a shaft going through the gear, right? So what does the shaft feel due to this carriage of the gear? It feel this force here, right? It also feel what? The torque at here, right? So you have basically two things at here. Then for the shaft design later, so what you're going to focus on is that basically it's going to be the FA, okay, and the TA, right? But you know, when you look at the FATA, so actually we can also see it. Where does the FATA, where are they from, right? The TA is from where? From the WT, right? WT. So you can see it's WT. And FA from WR and the WT. So you can call it this basically, you should just focus on WR, WT, that would be fine, right? Yeah. So the WR and the WT, it's like a two-plane. You know, one goes this plane, the other goes this plane. So there's basically like a two-plane bending case, as we were dealing with in terms of the failure analysis. Okay. Yeah. So you can draw free body diagram similarly for the gear. Okay. Just reverse directions, right? It's the same thing. It's okay. Yeah. WT at here, we have a name. We call it the transmitted load. And WR here is called the radial load. Okay, the radial load. So the radial load doesn't generate any torque, right? Yeah. Okay, so the T, as you can see now in this case, the TA in terms of the WT, that should equal to what? Times the half of the diameter, right? That'll be your torque. Yeah. And as we're going to learn next, we also often in time when you design, you'll be given certain horsepowers, you know, a power, okay, desired power output, or you know, for the system. So for the power H transmitted by the gear, it's basically torque time the angular velocity omega. Okay. Yeah. So you can put these two together. Okay. So that's your power transmitted. Okay. From one gear to another. Okay, can be calculated using this one here. Okay. Okay. Now, when we learn helical gear, there's an axial load, but we'll look at that. So basically, there's going to be another symbol called WA there. Okay. Yeah. Any questions on Spur Gear? No good. All right. So the helical gear. Okay. Before we look at the helical gear force, we have to go through a certain set of terminologies for helical gear. Okay. So I'm gonna open up a file here to grab a picture. Okay, so this is the picture I wanted to grab it here. Okay, so helical gear is different. The reason, obviously, because the teeth is not straight, it's inclined, right? Yeah. Now, what's the nature of this helical gear? So there are slightly different terminologies in terms of helical gear here. I'll just quickly go through these things that are here. Okay? Yeah. So here it's actually they use a diagram called helical rack. Okay, so the teeth here is inclined, but it's not the curvature. But in practice, when it's helical gear, as I was telling you in the introduction, so if you have a cylinder here, then you generate basically a helical curve, right? And that helical gear tooth is just a portion of this helical curve. All right? Yeah. So when it comes to helical curve, there are a couple of properties in terms of helical curve. Right? One of the property is, okay, if you draw a center axis at here, and then you can always draw, let's say, a tangent vector, okay, to this helical gear, to the helical curve, okay, and then this tangent vector will form an angle with the vertical axis, right? So with the rotational axis, okay. That angle is actually a constant. So if you're really interested, you can easily derive that. If you recall that in the parametric equation for helical gear, the parametric equation is a cosine t and a sine t and bt. Okay, that's helical gear, right? So you can see if you only look at x or y, it's a circle, and then look at z direction, it goes up, right? Yeah. So you can calculate this t as dr over dt, the derivative. That's the tangent vector. And then this t will form a constant angle between the vertical axis. Let's say it's a z-axis. Okay, yeah. That angle can be calculated, which is this. Okay, which is this. So that's the constant angle between the tangential vector and the vertical axis. All right, yeah. So in this particular case, it's basically it's an angle between this inclined line and this vertical axis, right? And that angle is what we call the helix angle. Okay, so that's one particular angle associated with the helical gear. So this phi here, so I think I should use a different symbol here because I use a pressure angle for this, right? So I use this. Okay, that's the pressure. That's the helix angle. Okay, that's a helix angle. You can easily calculate. You can use the dot product to get this angle here. Okay, yeah. Okay, so now when it comes to helical gear, if you imagine this, right? If you look into this AA plane, basically, if you look at it right at the front plane of the gear, right? You see a whole bunch of gear teeth. Is that right? Yeah. And if you cut this, the gear, helical gear, with a plane, this BB plane, and that BB plane is basically a plane perpendicular to this gear tooth, okay, normal to the gear tooth. Or in other words, actually, you cut it at an angle of the helix angle here. Okay, see this line and this line here, right together, you have a helix angle. Okay, yeah. So if you look at it, if you cut it, okay, my computer is a bit slow. In the past, I could be able to show you. Basically, when you cut it, you do a section view, then you project yourself into the section, the cross section, right? Guess what? You will see another basically circle, right? With a whole bunch of gears on the circle. Can you imagine that, right? So the two different views, right? You have a two different kind of circle, just as if you have a two different kind of gears. So when you look at the front view here, if you just look at the gear tooth, it's nothing different from spur gear. Okay? And you forget about the how the teeth goes, right? Just look at the tooth profile, everything else. It's the same thing as the spur gear. Alright? Yeah. And if you cut it to look at the BB plane, it's the same thing. You see another set basically like a spur gear essentially. You see what I'm saying, right? Yeah. However, right, because the two different views are different, so essentially what we really end up with, we end up with two set of sort of like a gear parameters. You know what I'm saying, right? So what are the gear parameters? We have the diametral pitch, right? We have pressure angle. We have the number of T's, stuff like that, right? Yeah. So you look at the different views, you get a different gear parameters, the circular pitch, things. So basically, we just need to figure out this different set of parameters that are here for the two different views. All right? Yeah. So let me maybe expand this one here a little bit here, just to be bigger. Okay. So for example, right? This one here is the front view. So that front view is what we call the transverse. Okay, this is the AA, and then for the BB is what we call the normal. Okay, it's a normal plane. Okay, so then there's a subscript T, a subscript N associated with the two planes that are here. All right, yeah. So let's say, for example, if I look at the transverse plane here. So let's say if I go from this location A. So this is a bit of a not very good drawing here, but you can imagine this. This is basically one T's and goes to a open area, and then go to another portion of another adjacent T's, right? Yeah. So from this A to the C location, as we actually learned in the gear terminology, we call that what? We call that the circular pitch, right? Basically, when you go from one point to the adjacent points. Okay? Yeah. So the AC over there, right, is basically I use a small pt. Okay, small pt. This is the circular pitch. Okay, on transverse here. Okay, on the transverse plane. So sometimes we can call it basically you can actually simply call it transverse circular pitch. Okay, just call it transverse circular pitch. Okay. So similarly, if you look at the into the BB plane, which this plane here. So then the adjacent point is from A to here now, right? So AE. So that'll be the PN will be the normal circular pitch. Okay, normal circular pitch. Yeah. The connection between these two geometrically, you can see that is connected by this. So the normal circular pitch equal to the transverse circular pitch times cosine helix angle psi. Okay, yeah. Helix angle can be different angles. Can be 10 degree, 12 degree, 20 degree, 25 degree, right? Doesn't matter. But you can imagine the higher helix angle means what? That helix will be inclined with a much more angle there, right? So there will be basically more capacity or more engagement in terms of the two gears. Okay, when you have a higher helix angle. Okay, so you can carry more load. You have a more smooth motion. However, as we're going to show you, so when the helix angle is bigger, then it'll generate a bigger axial loading along the shaft. Okay, along the shaft. Okay, so that's PT and PN. Okay, the pressure angle has also two sets here. One is phi t, one is phi n. Okay, one is phi t, phi n. So phi t is the transverse pressure angle. So that's the pressure angle in the transverse plane. And this is the normal, pressure angle. Okay, yeah, that's the pressure angle in the normal plane. So this is the pressure angle, for example, In this plane, you have pressure angle. Okay, and in the BB plane, you have another pressure angle essentially. All right, yeah. And they are different, but they are connected. Many things are connected here. So, but first of all, these two are not the same. Okay. So, what's the connection? Here is it. The cosine helix angle equal, okay, tan phi n over tan phi t. Okay, so that's the connection. Yeah. So you see the three angles, right? They're connected using this formula. Okay. If you want to prove, you can come to me, but you're just pretty straightforward proof on the using geometry basically. All right. Yeah. So if you want to use a CAD software to create a helical gear properly, then the helical curve needs to be generated properly. Okay, to guarantee that the helix angle is properly. Okay. So there's an example in the lecture. You can take a look at that. I'll skip the lecture there. Right? Yeah. So I'll just jump into the last point, which is the force analysis for helical gear. So I'm going to grab this diagram right here. Okay, so you have a helical gear right here. As we said, the helical gear has a helix there. So the action-reaction force, which is W, just the same symbol as the spur gear. Imagine there's another one on the top there, right? It's going to be perpendicular, okay, to the surface it's acting on. That makes sense, right? Yeah, perpendicular surface acts on. Now, this is actually basically, if this is the gear here, and it's acting here, it's not basically in the same plane as this front view, okay? Not in the same plane. So we can basically decompose the W into three different vectors. One goes down, that's the radial. The other goes horizontally, that's the tangential. And the other one goes the same direction as the z-axis or the x or the shaft, right? Or the shaft, okay? So the WA right here is what we call the axial loading, okay? The axial loading, WA. So it's like you have a shaft here, and then there's a force, right? Trying to push the shaft, basically in this direction, the axial direction, right? So if you have a force pushing this way, then guess what? You're going to have something to stop it from being pushed away, right? And that something is going to be the bearing, the bearing that can carry certain thrust load, okay, to stop the shaft from being pushed away, okay. Yeah. But that does add a certain level of challenge in terms of shaft design, because not only you have these two now, you have this one now. So what are the angles now, right? The W, between the W and the horizontal plane, this is the pressure angle in the normal plane. And between this horizontal line, this one here, that's the helix angle. And between these two, this is the pressure angle in the transverse plane. Okay? Yeah. So based on this geometry right here, and you will be able to, let's say, derive certain connections at here, right? Certain connections. So let's say if W is known, okay? If W is known, so what are each one of the components, right? So WR equal to W sine phi n. Is that right? Yeah, right? So you look at this plane here, and that's the phi n. So WR times sine give you this WR, right? Give WR. Thank you. And WT equal to W times cosine phi n and cosine psi. Okay. And WA is W times cosine phi n times sine psi. This is very much like a spherical coordinates, if you recall that. Okay, yeah. decompose that using spherical coordinates. Okay. So anyhow, but often in time, what you know is you probably actually your starting point is WT. Okay, starting point is WT. Why is that? Is because the user will give you is a horsepower. They tell you, hey, this is how much horsepower I want it to be able to carry, right? Okay, and this is the angular the velocity, the shaft I want it to rotate, right? So based on these two information, you're going to be able to calculate what will be the transmitted load. Then from the transmitted load, you can back calculate W and WR and WA. Okay, so pretty simple. Just manipulate the three equations. You can get the different set of equations. Okay, so you can go back to notes. So any questions? Okay, so now we're starting from next week. We'll start to look at the design for gear. Okay, yeah.